Okay, so having studied a couple of families of molecular anions, the dipole bound and the double Rydberg, let's move on now to another couple of families that involve multiply charged anions. And the first species group that I want to talk about are these dicarboxylate dianions that were studied by Lai-Sheng Wang's group in the early 2000s. And what they did here is they formed these doubly charged dianions, carboxylate group, methylene spacers, carboxylate group, with various numbers of methylene spacers. They form these in the gas phase, so they have some reason to believe that the geometrical structure of these species is somewhat extended because these two anionic ends of the molecule push one another apart. And they measured the electron binding energy by shining in laser light and seeing what kind of frequency of light, what kind of energy was required to remove that electron or that electron. And by measuring these electron binding energies as a function of the number of methylene spacers here, they gathered the following kind of data. For very large numbers of methylene spacers, that is long chain lengths, they obtained high electron binding energies. And as the number of methylene spacers got smaller and smaller and smaller and smaller, so these two anionic sites got closer and closer together, the electron binding energies fell off. And they fell off in a quasi-linear fashion when plotted as a function of 1 over the distance between this end of the molecule and that end of the molecule. This 1 over distance would be hinting to you something about Coulomb potential here. Okay, well, let's pursue this a little bit further. If they took this data, and they took the data for example, 10 methylene units and 9 and 8 and so forth, and extrapolated backward to 1 over r equals 0, that is r equals infinity, that means essentially a very long chain, they find an extrapolated value of about 3.2 EVs. This is very similar to the electron binding energy that would exist in, for example, this monoanion. That makes sense that if these two anions are far apart, removing an electron from this end or that end, doesn't even know the other end's there, it should behave similar to this monoanion. But then they saw that the things fit this 1 over r potential for this 1 over r shape. And that is for anything larger than 2 methylene spacers in there. And if you want to express the Coulombic interaction of two charges that are a distance r in angstroms apart, and you want that energy to come out in electron volts, the formula is 14.4 EVs divided by r angstrom. And this graph basically did fit that formula to a pretty decent level of precision. So this suggests the following model. It suggests basically that to remove an electron from there costs you 3.2 EVs, except this charge over here can, in a sense, help to destabilize this electron over here by an amount that is 14.4 over r. So it suggests a formula where the electron binding energy equals an intrinsic value minus the Coulomb repulsion of the electron you're trying to pull away with the other excess negative charge in the system. This Coulomb repulsion model is going to come back to be discussed several other times later in this series of videos. So please keep that in mind, 14.4 over r. Another thing, though, that I want to stress here is that there isn't any data for fewer than 3 methylene units. Why? Because they couldn't form the dianion with 2 or 1 methylene unit in there. That suggests that there's something unstable about the dianion when you go to 2 methylene units. And for example, this suggests that the electron binding energy, if I were to extrapolate that out and go to 2 units, that I might actually have an electron binding energy below 0. And that's indicative, remember, of this plot I talked about earlier for multiply charged anions. If you're that electron and there's a very short spacer in here and you feel this negative charge over here, you feel a repulsion until you feel an attraction that binds you. But if that repulsion is too strong, that bound state might actually be pushed up above 0 and may not even be bound anymore. Now, an example of exactly that. Another set of experiments that the Lai-Sheng Wang's group did was to study this phthalocyanine. So here we have a copper atom surrounded by this phthalocyanine planar conjugated aromatic system. And they made this phthalocyanine with either 0, 1, 2, 3, or 4 sulfonate groups out on the periphery. The important thing is these sulfonate groups are negatively charged. So what they did is they took the phthalocyanine with no sulfonate groups and the copper in the middle, and they essentially said, okay, if I shine a laser light in, how much energy do I need to pull an electron off this copper atom, that is to ionize it? And they did that experiment and they found 6.3 EVs. When they then repeated the experiment with the copper phthalocyanine with, for example, 3 sulfonate groups out there, what do you expect? Well, this electron here now feels 1, 2, 3 negative charges pushing it up. There's destabilizing it. So it ought to be destabilized by 6.3. It ought to have an ionization potential of 6.3 EVs minus its Coulomb interaction with this, and with this. And indeed, when you study the photoelectron spectrum of this species, 3-, what you find is that to detach an electron costs 1.2 EVs. Now, it's a little, so the difference, the 5.1 EVs, would be the Coulomb interactions within this Coulomb model here and here and here added up. But there's something else. If they shined a laser in there whose energy was only 1.2 EVs, they did not see electrons coming out. They had to shine a laser in there with an energy that was 1.2 EVs plus 2.5 EVs, that is 3.7 EVs. Now, why'd they have to do that? Because this Coulomb repulsion barrier that I talked about, remember the idea was that when you're a multiply charged anion, there's a barrier and then there's an attractive potential. That barrier there causes the electron, if you start out here with the triply charged anion and shine in a laser light of only 1.2 EV, in principle you have enough energy to remove the electron, but it has to tunnel through that barrier. And that tunneling might take a long time if this barrier is thick and or high. So they find that when they tune their laser up beyond 1.2 EV, 1.5, 1.7, 2, 2.5, eventually 3.7, then they see electrons coming out like a bat out of heck. So they're able to measure the electron binding energy and the height of this repulsive Coulomb barrier. Now the magic. When they did the experiment with the phthalocyanine with 4 sulfonates out there, they found that when they shined in light of 0 energy, nothing, 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 they had to shine in light of energy 3.5 EVs, and magically, when they measured the kinetic energies of the electrons that were coming out, the electrons had kinetic energy of 4.4 EVs. So they're shining in light of 3.5 EV energy, and out comes electrons moving at 4.4 EVs. That means the electron was unbound. That is, it had an energy that was unstable relative to a free electron not moving by 0.9 EVs. So this quadruply charged negative ion actually is unstable. Its electron is not actually even bound, but it's trapped behind this repulsive barrier that's so thick and high the electron can't get out, even over periods of seconds and minutes. They had to excite it up above the barrier to remove the electron. So that's an example of these multiply charged anions giving really strange behavior. Let's look at another one. MgF4 double minus. Now, MgF4 double minus is isoelectronic with SiF4, very stable object. You can think of it, if you want to think of it in terms of ionic bonding, as an Mg+2 cation surrounded by 4 F- anions. Now, if you think of it that way in particular, it's sort of useful to imagine it this way, because one would imagine then that if you had the species existing like this at a certain geometry, say it's equilibrium geometry, to remove an electron from MgF4-2 to form MgF4-1 plus an electron should cost a certain amount of energy, and that amount of energy you would expect to be less than the amount to pull the next electron off the second fluoride, because to pull the electron off the second fluoride, it doesn't get destabilized by the presence of so many fluorides. That is, the difference between 2- going to 1-, which we calculated to be 2.6 EVs, should be less than the energy going from 1- to 0, 7.1 EVs, and the amount by which these two differ, 4.5 EVs, should have something to do with the Coulombic repulsion between the electron removed, say, from this first fluoride compared to the electron removed from the second fluoride. See, in the first fluoride, when you remove the electron, it gets destabilized by 1, 2, 3 other F-. But when we remove the electron from the second fluoride, it gets destabilized by only 1, 2 other F-. So one extra F-F interaction are there. So it turns out that the equilibrium geometry of this species is such that its distance divided into 14.4 EVs is 4.5 EVs, sorry, 14.4 divided by R in angstrom, R being the FF distance, 4.5 EVs. That is indeed the difference between this ionization and that ionization. So this Coulomb model is holding up here. Now there's some experiments where there's another series of calculations that we did on another ion that's tellurium that has a square of 4 fluorides above it and a square of 4 fluorides below it that have been twisted by a little bit. So TeF8 double minus, that dianion has an electron binding energy for its second electron. See this second electron here is 2.6 EVs. The second electron binding energy in this species is 5 EVs. So I'm saying this so you don't get the opinion that these doubly charged anions always have to have low second electron binding energies. They can have very large electron binding energies. The second electron, of course, will be bound less tightly than the first electron. Now let's compare MgF4 double minus, which we just talked about, with SO4 double minus. What do you think is about SO4 double minus? Let's talk about that a bit. So here's SO4 minus 2. If you think of it in terms of this ionic binding, it would be like this. Now in this case, there's a difference between the Mg and the SO4, because in the case of sulfate, the oxygen-oxygen distance in the sulfate dianion is shorter. So the repulsion between two oxygen centers in the SO4 double minus is 5.88 EVs, whereas we saw a little while ago in the MgF4 double minus, the FF Coulomb repulsion was 4.5 EVs. So in the case of the sulfate dianion, you have stronger Coulomb repulsion between the ligands, and the ligands are oxygens, not fluorines. So the intrinsic binding energy of the ligand is a little weaker. So in the case of the sulfate, it turns out that unlike the MgF4 double minus, the second electron is actually not even bound. That is, the second electron affinity, SO4 minus attaching its second electron, doesn't have a second positive electron affinity. As a result, we say sulfate, phosphate's the same actually. The phosphate trianion and the sulfate dianion are two such dianions that are really unstable. That is, they don't even exist in the gas phase. There is no SO4 double minus. There is no phosphate triply minus in the gas phase because the outermost electron is unbound. Whoa, now that's sort of weird, isn't it? So you say, well, how unbound are they, and is there any evidence for this? First of all, let's talk about evidence. There are some experiments, again done in Liesheng Wang's group, where they've taken sulfate dianions and they've clustered them with water molecules, 13 waters, 12, 11, 10, 9, blah, blah, blah. And for example, they measure the electron binding energy, either vertical or adiabatic, of the, for example, in the case of 11 water molecules attached to the sulfate anion, it takes about 3-ish electron volts to pull an electron off that SO4 minus with 11 waters. When they do it for 7 waters, it takes about 2-ish. When they do it for 3 waters, it takes about 0.2 or 0.3-ish. So when they graph up their data, so these are the data, these points here are not real points, they're just extrapolations. When they graph up these data here, they find that for 3 water molecules and more, the electron actually is bound. But they can't form SO4 minus with 1 water or 2 water molecules. Why? Probably because it's unbound, like we're saying. Moreover, if you were to try to extrapolate their data with, say, 5 waters, 4 waters, 3 waters, and try to say what should it be for no waters, it should be about this -1 that we're talking about here. So this is just some experimental data that shows that, yeah, probably sulfates with 0 or 1 water even probably aren't really bound. So what did we do to study these things? Well, we carried out some calculations, and these are what are called stabilization calculations, where what we do is the following. We take the sulfate anion, and we take its nuclear charge of the sulfur, and we change it from being 16 to 16.1 or 16.2 or 16.3 or 16.8. So we actually, in a sense, increase the local attractive valence potential that is trying to attract that second electron into the sulfate anion's region of space artificially. and we calculate the electron binding energy, that is the energy difference between SO4 double minus and SO4 minus at the same geometry, that is the geometry of the sulfate dianion itself in a crystal. And we calculate this electron binding energy as a function of this nuclear charge. So for example, for 16.7 nuclear charge at the MP2 level, MP4 couple cluster or Hartree-Fock level, the electron binding energies are up in the 6-7 eV range. For 16.6 nuclear charge, they're in this range at different levels of theory. We calculate that until we get down to electron binding energies that are 0 and below. We don't trust the values 0 and below because that's unbound. So we take these energies, for example, the MP2 energies, here, 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 and here, and even here, they're still bound, and then we extrapolate them down to 16.0 as the nuclear charge. And when we do that extrapolation, we find that the dianion is unstable relative to the anion at, for example, the couple cluster level of theory by 1.1 EVs, at the Hartree-Fock level of theory by, say, 1.7 EVs. So we were able, with these stabilization calculations, actually to estimate the energies of these unstable species. Okay, that's, I think, enough for this particular section, so I'm going to end this one, and then we'll move on to the next section.